Okay, hello everyone. Welcome back to your YouTube channel. And today I have a very interesting and amazing video for you. As you must be aware, my master students, they are creating a test system from scratch. And one of the issues that they are facing, well, it's not an issue, but it's a confusion. One of the confusions that they have is related with the phase angle between the high and low voltage size in this star delta or delta star transformer. Also, I received a couple emails from YouTube users asking me about the same issue. And for that reason, I decided to create this very short video to show you the fundamental aspects of modeling the phase shift in a delta star transformer, okay? Especially inside the DIgSILET PowerFactory. If you remember, 1 week ago, I published a video regarding a phase shift transformer, delta star transformer, and I published specifically the results for this transformer between bus bar 9 and bus bar 1. This is a transformer. As you can see, the transformer, the low voltage side is 15.5 kV and the high voltage side is 230 kV. When we run the load flow, the classical positive sequence load flow inside the DIgSILET PowerFactory, we get the voltage here on the high voltage side, and this is 0.99 minus 4.1 degree. And the voltage on the low voltage side is the reference 1.0 at 0 degree. Um, I received a couple emails and people ask me, okay, if you are using a vector group that is delta star 0, what is the reason that you got a minus 4.11 degrees phase angle at the high voltage side? And a couple people ask me, if you are using a delta star connection 0 degree, zero phase shift, where this minus 4.15 degrees is coming from. Okay, this is a very interesting question. However, what you need to remember is the basic of modeling. Okay, time to time, people focus on just using PowerFactory and put numbers and get results, and that's all. And that is my main complaint about some aspect of the educational system. We need to understand clearly modeling in order to explain results. Okay, what I will do is something very simple and show you in a very simple way where this minus 4.11 degrees is coming from. The first thing that you need to understand is the model that is located inside the DIgSILET PowerFactory. If you go to the technical reference of the two-winding transformer, the three-phase two-winding transformer, at section 1, you will find the model for the positive and negative sequence, okay? In this case, I am running a classical positive sequence load flow, symmetrical and balanced load flow. As a consequence, I will focus only in this figure number 1. That is the positive sequence equivalent model for the two-winding transformer. If you look over here, this is the positive sequence model for the two-winding transformer. In this case, this is per unit. Okay, in this case, this is per unit. Of course, we are working with a three-phase transformer, but this model is one of the phase. Okay, but the important part here is that you must understand clearly this model. If you remember your classes from electrical machines, you must remember that a transformer has basically some passive component inside. You have resistance and inductive reactance in the high voltage. You have resistor and inductive reactance on the low voltage side. And that is basically the series impedance. And then we have here the shunt branch that is basically to represent some losses inside the transformer coming from the core and so on, okay? But my most important aspect here is the transformer. This is an ideal transformer. If you go to the technical reference, you can read the ideal transformer has a complex winding ratio with a magnitude of 1 to 1 and models the phase shift representing the vector group of the two windings. What I'm trying to explain is this number here is a complex number. You must remember this is E exponent j phi. And if you put here 0 degree, if you put here 0 degree, this number is a real number and became 1. And 1 to 1 is basically a cable between the primary and secondary. But if you are using a delta star 11, for instance, this case, this phase angle here will be 30 degrees, okay? And now we have a phase shift between the high voltage and the low voltage side. What I'm trying to tell you is this ideal transformer is the key of the answer, because this ideal transformer is using a complex winding ratio or transformer ratio in order to represent the phase shift of the vector group, okay? And now what I will do is use those concepts. I will use those concepts to show you with numerical values. And it's extremely simple, okay? Let me come back here. If we assume that this transformer has not losses related to the core, we can remove this branch, okay? Then we have here the series impedance on the high voltage side, and we have here the series impedance on the low voltage side. We can move this impedance to one of the sides. It's okay, we can do that. It's extremely simple. And the other thing that we can assume is there are not copper losses on the windings, and as a consequence, those resistors will disappear. What I'm telling you is that this is the simplified version. This is the simplified version of the model that I showed you before. What I did is I removed the shunt branch because there are not losses in this transformer. I remove the resistance because there is not copper losses at the windings, and I lump all the reactance, inductive reactance in this one JXT, okay? And here you can see the ideal transformer. Now, what you need to understand is that when we are using DYN 0, the phase angle is 0, and this complex number here and this complex number here at the exponent here become 1. And as a consequence, you must remember 1 to 1 transformer ratio is equivalent to having just a cable here and a cable here, and this ideal transformer disappear, and finally we have this model over here. Okay, what I'm telling you is when we have a DYN 0, the phase angle is 0, these exponents become 1 per unit, one per unit, and then we can say, okay, 1 to 1 transformer is equivalent to disappear this transformer, and when we have here is this. I think it's extremely basic. This is just basic circuit theory, okay? I believe all of you can follow that. But now the question is, the most important question is, my students and some people ask me about this 4 degree, where this 4 degree is coming from. Well, what you need to understand is if we assume that this voltage is 1 per unit, and this is this voltage over here, there is a voltage drop across the transformer series reactance of this transformer, and that is creating this 4 degree. What I will do now is basically show you using circuit analysis, basic circuit analysis, this. Okay? If you remember, we are working with the transformer, and in this case, this is the transformer that we are working here, and this is DYN0. And the reactance, you can see over here, the reactance is already 0.12 per unit, okay? And this number is coming here. What I did is I used DIgSILET PowerFactory, and from DIgSILET PowerFactory, I get the per unit current, And you can see 0.611 per unit, and the angle of this current is minus 13.741 degrees, okay? Now what I will do is something basic. Everyone at the school can do that, and that is using Kirchhoff voltage law, to obtain this voltage here. And that is extremely simple, to be honest. And that is what I will do in the next slide. Here, what I am doing is using Kirchhoff voltage law. Sorry, I didn't include it. Let me say here, this is Kirchhoff voltage law. And we can obtain the voltage here in this terminal. This is the voltage that I want to calculate because I want to show to my students that this is the source of the minus 4.1, okay? I put here all the numbers together. Remember, this current is coming from PowerFactory. I got this current from PowerFactory. I create a MATLAB code. Sorry, I am a bit lazy lately. Well, not lazy. I don't have so much time to do it. And I use MATLAB, and voila, we get here the voltage at the high voltage side, 0.99 minus 4.1. Okay. Now we have demonstrate this 4.15 degrees, and that 4.15 degree, negative 4.15 degree, is coming basically up because the voltage drop across the series reactance in this transformer. Okay? Well, we demonstrate this, but now, probably to avoid the question, well, what has happened if we use the DYN11? Well, it's extremely simple, okay? Right now, what I will do is I will show you here the results. In this case, we are using a DYN11, and this DYN11, they are 30 degrees. They are 30 degrees. And this 30 degree is located here at the ideal transformer, okay? What I will do is now, again, use basic circuit analysis, but what you need to understand is that this voltage can be obtained using Kirchhoff voltage law in this side. If we use Kirchhoff voltage law, we can obtain the voltage here, and that is what I did, okay? Using basic circuit analysis, I obtain here the voltage V1, okay? V1 dot. But this voltage is located here. Then what I need to do is use the transformer ratio, and remember that the transformer ratio in this case has 30 degree, and voila, we can obtain the solution. And the solution here is 0.99 minus 34.1 degree per unit, okay? Well, this is an amazing explanation. I try to do my best. I try to show all the students and also my YouTube fans that we can explain any results inside PowerFactory. If you remember your classes from electrical machines, from power systems, okay? Every single calculation inside DIgSILET PowerFactory, there is an equation behind, okay? Every single result have a theoretical explanation. For that reason, I highly suggest my student, I highly suggest to every single of my YouTube fans and also everyone watching my videos, please try to do your best to understand the models. And if you understand the models and you can use the equation to explain the models, you will be very, very fine. You will be okay explaining your results. Well, this is all for this video today. It was a very short video. Thank you for watching. I will see you in the next video. Thank you. Bye now.